Hello, and welcome back to the General Physics Laboratory. This week, we are taking a detailed look at simple harmonic motion. There are many types of periodic motion, but not all are simple harmonic by nature. Simple harmonic motion is a special type of periodic motion where the position of the object varies sinusoidally. It is the result of any force that takes the form of Hooke's law, where the force is directly proportional to the object's displacement and tends to bring the object back to its equilibrium position. The force on a mass from a spring is a classic example of Hooke's law. When set into motion, the mass undergoes simple harmonic motion. To study the motion of a mass on a spring, we will suspend a mass on a spring vertically. Then we pull the mass downward a short distance and release. As it moves in simple harmonic motion, we measure the position of the mass. The motion detector provides a highly detailed position over time graph since it can measure the position of the mass hundreds of times per second. We let the mass move through a few cycles, and this is the only data set we need for this experiment. We use our motion sensor data to compare the values of the mass's position, velocity, and acceleration at different points in time. For example, the points on your position versus time graphs, where the position is 0, signifies that the mass is passing through its equilibrium position. At these same points in time, you should notice that the mass's velocity is at a maximum and that its acceleration is 0. We can also compare these value points in time when the position is at its highest or lowest values. These events occur to the mass being at the extreme ends of its periodic motion. At these points in time, you should observe that the velocity is 0 since the object is turning around here. You will also observe that the acceleration is at a minimum or maximum since the spring is pulling hardest at these points. Similarly, we can use the values of position and velocity to calculate the kinetic energy, potential energy, and total mechanic energy of the system at all points in time. When the mass passes through its equilibrium position, all of the system's energy will be in the form of kinetic energy. Meanwhile, as the mass stops briefly at its maximum positions, it will have no kinetic energy, and all energy will be contained in the potential energy stored in the stretching and compressing of the spring. Overall, we expect that the system trades potential energy for kinetic energy back and forth while the total energy is conserved.